This is the Insurance Institute for Business and Home Safety's Disaster Discussions podcast, where we explore the intersection of weather and the built environment. Welcome to the Disaster Discussions podcast, where we explore the intersection of weather and the built environment. I'm your host, Rachel Penton-Goche. It's a project that's been years in the making, the In-situ Collaborative Experiment for the Collection of Hail in the Plains, or ICECHIP for short. The first scientific field campaign in decades dedicated to studying hailstorms. This project will aim to improve radar detection and monitoring of hail, provide critical ground truth information for materials science, and improve the nation's capabilities to predict hailstorms and their impacts, a peril responsible for billions in insured losses every year. 15 institutions and 4 international partners, including approximately 90 students, researchers, and professionals, will traverse the plains for 6 weeks chasing hail-producing thunderstorms, including the IBHS hail field teams who will be deploying disdrometers within a network of mobile instruments, leveraging modern technology to revolutionize what we know about hail. Ahead of the deployment, ICECHIP teams convened in Boulder, Colorado for campaign training, media interviews, and a field date for the public to meet the scientists and see the technology headed into the field. IBHS was there and had the chance to talk with some of the key players in this project about what they're hoping to accomplish. First up, my teammate, meteorologist and science content producer, Christina Gropp. She talks with research meteorologist Dr. Ian Jemenko and Brenna Meisenzahl about IBHS's role in ICECHIP.
This is a huge project. Give us a quick overview of all of the 19 organizations coming together.
Yeah, so we've got 15 organizations for the United States here that represents, academic institutions, the government labs, and then we've got another set of international partners who are participating in the project, really with the entire goal to study hailstorms in detail that we've never been able to. So everything from the environment these storms are in, all the way down to things like how strong are the hailstones. So we're going from the big all the way down to the really small and everywhere in between.
The IBHS members have funded our field campaign year after year for more than a decade now. And Brenna, this year, we are embedded within this larger project that's going to allow us not only to capture the data that our members are so used to us capturing, but to capture so much more. Talk a little bit about what we are doing as a part of this huge multi-institutional project.
Yeah, so we are part of the ground team. So we will be using our fleet of impact disdrometers to collect swath data and also concentrations of hailstones. And then we will also be doing physical measurements as we typically do, where we get diameter, mass, and we do crush tests of stones to get the strength data. We will also possibly be doing some 3D scanning of stones as well as cross-section of stones as well.
Those pieces all depend on the storms to come together to give us the right hail, but that's the goal, right? To get all of that data on the same storm. And Ian, we couple that with all of the other data that other teams will be collecting that we don't normally get to collect when we just have our IBHS field project. How transformational is that going to be?
Yeah, so the biggest example of that is take the balloon sounding teams, where we're going to surround these storms and launch weather balloons around them. We're also going to have smaller ones that actually go into the updraft of these storms. So the one piece that we've been missing when you think about all the hailstones we've crushed is having that environmental data. We know in the broad sense that the environment has a role in how strong hailstones are when they get to the ground, but we're going to actually be able to see that because we have so much environmental information about what the storm is embedded in. And we've got 6 teams doing crush tests, underneath these thunderstorms of all the hailstones that come out of them. So we're going to get this really neat view of how the environments influence the material properties of those hailstones. So that's just one example of how our data relies on some of the other data collected by ICECHIP and vice versa.
Now, Ian, the last time there was a field campaign, federally funded field campaign dedicated to hail, it was 40 years ago.
So if we rewind the clock, so the National Hail Research Experiment ended in 1978. I was not even born in 1978. And I think we do have one scientist participating in ICECHIP, Dr. Andy Heimsfeld, who was on that original NHRE experiment. But if we fast forward to today and look back even just over the history of our field program going back to 2012, you're over $250 billion in damage caused by hail. And you sit there and it's like head scratcher, like, why haven't we done this sooner as a whole? I think our members and IBHS have helped raise the awareness around the financial impact of this particular hazard to the point where we just cannot ignore it as globally in the science world. And we need to do things like this project to try to understand all the elements that come with hailstorms.
The research that our members have supported for years has really helped fuel this resurgence in hail research.
Next, we speak with Dr. Victor Gensini, one of the project's principal investigators and a professor at Northern Illinois University. Gensini spoke with us about changing hail environments and their connection to climate change.
One of the things we really need to know are some of these hail environments. So when a hailstorm forms, what's the temperature nearby? What's the wind speed, the wind direction, pressure, humidity, all these things that meteorologists care about. Those sort of environmental conditions we can track in climate models, we can track in forecast models, and we can look at their long-term trends. So what's the trend in moisture? What's the trend in instability and wind speed? And then the future projection angle, the climate models that help us understand these convective environments. That's really the key aspect and factor of trying to understand the future of these types of hailstorms. And we've done a little bit of research that suggests larger hailstones in the future, but maybe fewer small hailstones because of these strong updrafts that we're watching in thunderstorms. One of the things we've seen specifically really over the last 20 years is just an increasing number of these billion-dollar hail disasters. All over the US, it's not focused in one particular area, but it's really a function of kind of two things. We're seeing more intense and larger hailstorms in some areas of the country, and we're also seeing this increase in exposure. So a lot more buildings, a lot more assets along the ground that are being impacted by these hailstorms. And the result is really a twofold, in some cases threefold increase in some of the billion-dollar hail losses that we've seen over the last 20 years. And obviously, big problem from insurance, agriculture, logistics perspective, all of these, potential sectors that are important and impacted by hail. We have two really distinct instrument packages. We're actually working with IBHS to deploy shingle panels. So we want to know exactly how some of these new and upcoming materials are going to fare when we get hit by softballs or baseball-sized hail. The other aspect of our team is really measuring those environmental conditions that I mentioned. So we'll be launching weather balloons that will measure temperature, pressure, humidity, wind speed, and then we can then use those later on in our forecast models to initialize the models with those parameters and see how the forecast hailstorms in those models change as we have varying degrees of weather conditions.
NIU teams will be deploying IBHS roofing panels during the project to learn how hail can impact various materials.
All right, so we have 4 different classes and styles of shingles, some new emerging materials. Those are on top. We'll deploy one of those panels. We actually also have a metal roof. We want to see how the metal responds in some of the largest hail to see if it is possible to puncture or damage, not just aesthetics damage, right? We're interested in actual functionality of some of these panels. So we're gonna go ahead and take one of the top shingle panels out so you can see what this looks like. I have a grad student here, help me out. So we will basically bring this panel and hopefully put it in the path of the storm. It has basically small legs, as if the slope of the roof was an actual roof, right? And so you can see this particular panel that we have, doesn't look like normal shingles. This is a sort of high grade. We're hopeful that these types of panels can take 2-inch or even 3-inch hail. But we're going to see how these materials respond, very important for material science and new emerging roof materials.
We also spoke with another principal investigator, Dr. John Allen of Central Michigan University, who told us about the importance of mapping hail swaths for our built environment.
So under a supercell thunderstorm, they're carrying vast amounts of water up into the atmosphere. As that water falls, some of it's falling as liquid precipitation, what we call rain. More of it is falling as hailstones, these balls of ice that are falling towards the surface. Now, a hail swath is constructed by the accumulation of hail over an area of perhaps 2 to 5 miles in width, of various different sizes. Now, some of that hail is going to be very large, some of it is going to be small, and then it can persist as the storm tracks across the landscape. So some of these hail swaths can extend for hundreds of miles. So it's a very wide array of area that is actually potentially impacted for hail, and it's very relevant to agriculture and the built environment. So one of the issues we have with hail observations is that we only really get the biggest stone, maybe the thing that happens to hit somebody who's present. So we really don't get a full representation of what is actually happening inside a hailstorm and what is actually hitting the ground. Now, translate this into the urban environment. If you have that falling over a populated area, certain houses are going to get damaged, others are not. So without that information about the swath, we really can't know how the hail is distributed, how its properties vary, how much damage is likely within an area, how we warn for certain areas over another area. Are we going to get really intense hail over a couple of 100 meters and then spread further or spread much further than that?
CMU teams will be working closely with IBHS to deploy arrays of impact astrometers and hail pads to capture data within those hail swaths.
We're going to deploy a heck of a lot of instruments. So what we're really going for is a wide array of different instrument platforms. Some of them are going to sense hail impacts as they're occurring and sample them over time. Those are the distrometers. Some of them are there just to let us know if there was the presence of hail. So we have a series of foam hail pads, which are basically devices that measure hail impacts on the surface. They damage the surface. When we know that damage has occurred, we know a hailstone has occurred there. So we can get an idea of how wide this hail swath is, and we can deploy those for arrays up to 8 miles in width, which is a pretty large area, but some hailstorms do produce very wide arrays of hail. In addition to that, we have a series of mesonets and other pod-deployed instruments which are going to measure near-surface conditions, wind speeds, and similar things to know about how hail falls on an angle. Sometimes hail doesn't just fall straight from the sky, it gets blown by the storm or swung around the edge of the storm. What excites me most about for ICECHIP is getting in front of a very large supercell storm that produces giant hail, like really big state record stuff.
IBHS's lead research meteorologist and ICECHIP steering committee member Dr. Ian Jemenko caught up with principal investigator Dr. Becky Adams-Seelan of Atmospheric and Environmental Research at the field day to talk about some of the high-tech instrumentation.
Becky is one of the lead investigators and has been working to pull this entire project off for what we've been going on almost 6 years, right? All right, Becky, this is our sumo station. Tell us a little bit about it.
All right. Do you want me to hold it?
I got it.
All right.
I got it.
The SUMO, or Super Mobile Hail Observatory, was designed by the Canadian National Northern Hail Project. We were able to ship several of them down, and some of our researchers came with us. So basically what you've got is a large funnel with a handy kind of rubber type of material here. You would be surprised how difficult it is to get the correct material and height of funnel so that, number one, the hail doesn't shatter, and number two, it doesn't bounce out. Hail likes to bounce. So yes, they've tested it with a bunch of different range of sizes. It falls down in here. You see a lot of holes because it separates out the rain. And then we come all the way down to the bottom to our battery-powered mobile freezer. So if all goes as it's supposed to, we stick 4 of these out in the storm. We get out of the way, and then we come back, and our large freezer full of collected hail just happens to be nicely waiting for us. In addition to collecting the hail, we also have, this is a waveform radar. This measures the terminal velocity of the hailstones as they fall. Believe it or not, trying to connect the characteristics of the hailstone, if it's rough, if it's loamy, if it's squashed, any of these things, to how fast it falls. We are still it's hard to connect those things. So this will help us with our science. Also an anemometer, basic, but hey, if it's wind-blown hail versus just straight falling hail, you get a lot more damage. So yeah, we need to know how fast the wind is. Finally, good old-fashioned hail pad. I mean, old technology, but it's still great. If you want a full measure of the size distribution, hail pad gets you there. And finally, there's also a high-res camera and light up here. This can't tell us individual hailstones, but it can tell us, hey, roughly when did the hail start? When was it heaviest? When did it stop? That type of stuff.
So when we started this, right, we kind of called this our super station. It's meant to do everything in one spot that we actually wanted. Collect pristine hailstones, measure something with CW radar, get our wind data for wind-driven hail, and then, of course, use our traditional hail pad as our wonderful validation. So, Becky, thank you so much. And I will see her later once we hit the road.
Ian also spoke with Colorado State climatologist Russ Schumacher about the role of hail pads in ICECHIP and how the public can contribute valuable data.
He's got one of the old school measurement devices of hail. So Russ, I want you to talk to us a little bit about hail pads.
Yeah, this is very much the low tech part of ICECHIP, is making measurements with hail pads. But these are still some of the most complete way and robust way to measure hail when it falls is this very simple procedure of a piece of styrofoam, wrap it in heavy-duty aluminum foil, and then when the hail falls, it makes dents. You see how big the hail is, if it's coming in at an angle, how much there is, These obviously examples here are not the really big hail that the ICECHIP team is kind of most interested in, but certainly you could destroy one of these if you've got the 2-3 inch hail in there. So these are measurements that people can make in their backyards. Our role in the project is through what's called COCORAS, the Community Collaborative Rain, Hail, and Snow Network. It's a network of volunteers all around the country and around the world who make rainfall measurements most days, but then if hail falls, they can measure that as well and report it. And it's super helpful data for the researchers involved in ICECHIP to understand where the hail fell, where it didn't fall, how big it was, all of those kinds of things.
All right, thanks, Russ. I got one last question for you.
Yeah.
You got a chance to work with us a little bit on our Colorado State record hailstones, which I think you have one right here. So just talk to us a little bit about that process.
Yep. So this was the previous Colorado State record from 2019, 4.83 inches in diameter. And then this was surpassed by a hailstone that fell in 2023 in August that was 5.25 inches in diameter. And yeah, we've worked with Ian and the IBHS team to, get these 3D scans of these hailstones, which are obviously useful for your purposes very much, but these are also just a great educational tool, right? We've had the table here today, and the kids and the grown-ups come by and sort of marvel at how big this hail can be. And I think it raises awareness of the huge damage that hailstorms can cause, which are a big motivation for this project.
During ICECHIP, IBHS will be deploying instruments ahead of incoming hailstorms to take crucial measurements. I spoke with research meteorologist Jake Sorbert and instrument technician Lucas Faulkner about this technology and how it's going to be deployed in the field.
A distrometer, it's this piece of equipment right here, but it collects the impacts from the hail as it falls. They were calibrated in the lab, and as the hail falls and hits it, based on that calibration, we will be able to know the size and density of them.
And Jake, what's some of the additional data that we kind of learn as we deploy these out in the field? We put them in the path of hailstorms. We let the hail hit them. What types of things are we able to learn from this distrometer data?
Absolutely. So like Lucas said, we get size, but we can also look at the size distribution of those hailstones as they hit that distrometer. And then we have 24 of these, and so we can deploy them in an array on a road. So we get information about that size distribution across the hail swath, so the footprint of that hail, as well as the size distribution across that swath, not just that one local spot.
So we choose a storm, we decide to deploy on a storm. Take me through what happens as we say go, as far as the deployment of this distrometers. What does our setup look like?
So the setup is going to look like Jake mentioned. So they're going to be in an array down a street or a road, and basically these will be set up on the tripod like they are here and mounted there, and then they will be basically oriented towards the storm. And then so the switches on the front, they'll be flipped on. So there's a power switch and then a data switch. The power switch is flipped on, and then once there's a GPS fix, the data switch is fixed, and then they're good to go, and they can run for about 3 hours. And then so as the storm passes, it collects that data, and then after it's safe to return, we go back, and then we can collect the data.
And we're also capturing some pretty unique footage. We have some GoPros on these, and so we're able to kind of see those storms as they're coming, right?
Correct. Yeah. So the orientation, the GoPro will be facing towards the storm, so we can see that as it approaches the distrometers. And we can usually get some good footage of the hail falling before, and then some pretty cool shots after, like usually when the sun's setting, and some of them are pretty neat that way.
And you guys have really been helping out with some of the other teams. We've partnered with Central Michigan University. They're going to be deploying some of our distrometers as well. Just tell me a little bit about that partnership and what we're hoping to learn by working with them.
Absolutely. So by giving some of these probes to CMU and other universities, we can spread out the deployment region, right? And so we can have one team deploying on one road and then another team deploying on another road. Okay. And so it really gives us more of a wider net to deploy these distrometers, gather information about size distribution of hailstones, concentration of hailstones as that storm evolves and propagates over that array.
Yeah, we want to capture, even if there's some smaller stones on the kind of the outskirts of the storm, to maybe some bigger stones in that strongest portion of the storm. We want to capture really everything, right?
Right. The goal is to really just map out that hail swath as much as we can. And that's a lot of what ICECHIP is about, is mapping out these hail swaths and the environments that are conducive to these hail storms.
Right. And Lucas, you guys put a lot of work into this. A lot of folks back at the lab on our instrumentation teams. Talk about the work that went into preparing for such a big project and the people involved.
Yeah, so there was a lot of work that went into these. This year we did an overhaul on about half the fleet compared to last year. So there was a couple of the GPS chips were changed out. Some of the circuit boards in there, they were changed out. I want to give a big shout out to Heidi. She was the one that did a lot of the calibrations, and the calibrations are always a struggle that we deal with, especially with just the cannons and whatnot. They all have their own little personalities, we'll call them. So it takes a while to do that. Yeah.
And Rafi as well. I know he was instrumental in this.
Yes. Rafi helped a lot with this, especially on the code aspect, and then over here with the wind-driven hail sensor, he did a lot on that sensor as well.
Yeah. Speaking of that wind-driven hail sensor, this is a prototype, a new instrument. So we've learned a lot about hailstones falling directly at things, but we want to learn about all the different angles that hail can impact building materials and things like that. So tell me what this is, what you're hoping to learn with it this year.
Yeah. So to preface with the motivation for this sensor, like you said, we want to understand how a wind-driven hailstone is accelerated, how that kinetic energy increases, and how that impact angle changes. Right now, things like siding and windows, they don't have standard test methods that are meant to test these materials against hailstone impacts. And so in order to do that, we need to understand typical impact angles of hailstones and how those kinetic energies change in wind-driven environments. And so this is a sensor that's meant to do that. So that's it. This is a wind-driven hail sensor. And at the center of this sensor is a 6-axis load cell. And what it does is that when these hailstones hit the sphere here, the stainless steel sphere, it will detect the impact location. And so we'll have the force values and the moment values from that hailstone impact. And so based off of that, we can then back out impact angle of hailstones. So what we'll do is we'll deploy this in front of a storm, much like we deploy a distrometer in front of a storm. Like you said, it's a prototype. This is the only one we have, so we don't necessarily have an array. But the goal is to literally just back out that impact angle of hailstones and the kinetic energy and how that increases, so that we can then take that back to the lab and inform our testing on siding materials.
Right. So we're going to try to get this in some wind as well as some hail.
Right. So when you think about a thunderstorm, a supercell thunderstorm in particular, we want to deploy this near the mesocyclone, so on the southern side of that hail core, where you're most likely to have a wind-driven component to those hailstones.
And we have an anemometer as well.
Yes. So the anemometer is crucial, right? Because if we don't know the wind speed, we don't know how that wind speed affects the impact angle of hailstones. So if we have this anemometer, we can say for this wind speed, this is a typical impact angle for these hailstones. Ideally, we'll deploy this next to an impact distrometer, which is calibrated for size, so then we can have information about size distribution as well. Eventually, once we get to a final version of this instrument will be able to detect size distribution, kinetic energy, and impact angle.
IBHS will also be collecting valuable data on hailstones that fall to the ground, crushing, measuring, and documenting the characteristics of the stones, and possibly even 3D scanning some of the larger stones that may fall.
So starting in 2012, IBHS went out into the field with the goal of identifying characteristics of hailstones that need to be measured in the lab so that we can test building materials to those hailstones. And so what we ended up doing was we took out calipers, scales, and this piece of equipment here, a crush tester. And so I'll talk about how we run through and collect hailstones and do these different measurements. And so like you said, after the storm rolls through, we'll go back through and collect the sample size of hailstones, and then we'll measure them, weigh them, and crush them. And so we'll use these calipers, and we'll take maximum, minimum, and intermediate dimension of this, and then we will weigh it on our scale. And then once it's weighed and the measurements are taken, we'll put it on the crusher and we'll crush that hailstone, right? And so this is how that works. And then we have all that information about how hard that hailstone was, what are the size distributions of those hailstones. And that hardness of that hailstone, the compressive strength, matters because it controls what damage modes other building materials experience.
And we're, again, once again, getting a good sample size, anywhere from smaller stones to some of the bigger stones.
Absolutely, yeah. So the goal is to accurately represent the distribution of sizes at each location and how that changes from location to location, like we talked about with the impact astrometer.
And then for certain stones, we'll also 3D scan them. And this is a capability very unique to IBHS. We've developed this, and Lucas, you've kind of spearheaded some of this. Talk about how our 3D scanner works and what type of stones we're going to be looking to actually 3D scan out in the field.
Yeah, so for the 3D scanning scan stones, we're looking for the larger sizes. So usually it's roughly 2 inches or larger, especially those really unique looking stones like this one right here that has all these knobs on it, these weird shapes. We want to understand how these shapes become to be. So with the 3D scanner, we can take this right here and then actually get a 3D model representation of the stone. So we'll scan it top, bottom, and all the sides, and as it goes around, and then the laser, it picks up that surface area, and then we can basically make a virtual model of the stone, and then with that we can actually pull volume off of it. We can pull sizes and then compare that to the caliper sizes, and then
and we've used this also for some of our records as well. So not just collecting them out in the field on our annual project, but we've actually sent teams out to verify like record hailstones in different states. And this is actually a record right here, right? I believe this is Alabama.
Yes, I believe this was Alabama. So yes, we'll go out and do the same thing. And then if people out there, if they find these stones and they save them properly, putting them in a freezer bag and then into the freezer, we can go in and do that same thing and then measure these and then get those measurements off these stones and then hopefully get some records.
Yeah, and then we're able to recreate them by 3D printing them back at the lab. So Jake, talk about we gather all these different measurements along with the 3D scanning. How do we use this information? Why is this important? And it's going beyond just IBHS. Other research partners are able to use some of this information.
Absolutely. So with stones like this, just building off of what Lucas said, we can take these, print them to weight, and we can put them in vertical wind tunnels and study how they tumble and spin and move side to side as they're falling at terminal velocity. And then we can also take the 3D models and send them off to universities who then do backscatter calculations. Basically, how do weather radars see these hailstones? What they found is that just based off of how this hailstone is oriented in the air really influences how these weather radars see these large stones. And so with just radar alone, we don't have much skill at all at detecting the size of hailstones above 2 inches. And so it's really identifying key areas where the science can grow. And 3D scanning is really a watershed moment in hail science, the implementation of this technology.
And we want to learn more about the trajectories that these stones actually take throughout the thunderstorm before they make it down to the ground. Why is that important?
Absolutely. So when we talk about crushing hailstones at the ground, even at a single location, the crush strengths can vary widely between different hailstones. And crush strength doesn't necessarily depend on size. We think one of the variables that control crush strength is the amount of time that it spends below freezing in the hail growth zone, where that hail actually grows and lives before it falls to the ground. And so trajectories of hailstones really matter for understanding how compressive strength differs between hailstones and different areas within that storm.
ICECHIP teams will be traversing the Great Plains for 6 weeks through late June, traveling to wherever hailstorms are forecast. You can follow along on IBHS social media channels and with the ICECHIP tracker at icechip.niu.edu/tracker.
It was pretty amazing walking in yesterday and seeing everybody that is part of the global hail research community all in one spot. A lot of handshakes, a lot of hugs, a lot of big old smiles. It's really neat to see that the entire hail community is here and part of this. And that sort of speaks to this resurgence in hail research, that we've got this one great unified group of people that really does have the same mission.
This has been Disaster Discussions on the Radar. All hail the ICECHIP Field Campaign. Thanks for listening to the Disaster Discussions podcast. Join us next month for a new episode. For more on IBHS's ongoing research efforts, visit ibhs.org.